In this video, I'm going to be detailing the theory of continued fractions. We'll look at the definition of a continued fraction, infinite continued fractions, and three interesting results that come from the analysis of continued fractions. We'll look at an example first. Take the number 325 over 1346. This doesn't have a nice decimal representation. While it does repeat, it repeats with the period 224, so obviously we don't want to write that down. To write it as a continued fraction, first we take the reciprocal, so flip it and put a 1 above. Now in the denominator we have a top-heavy fraction, so we'll divide out the largest integer, which is 4. So now we're left with this remainder fraction, 46 over 325. We do the same process, we flip it, and then we divide out the largest integer. We continue until the remainder fraction is just a 1, so in this case we end up with 1/3. This is our first continued fraction. In fact, this is a simple continued fraction. The general form for a simple continued fraction looks like this, where all the partial numerators are 1, and all of the partial denominators are natural numbers greater than 0. We say a continued fraction is finite if it has a finite amount of partial denominators, otherwise we say it's an infinite continued fraction. There is also a popular alternative notation, this square bracket notation, which is much more compact. You might recognize this from sites like Wolfram Alpha. It only displays the partial denominators, as we know the partial numerators are all 1. You might ask what happens when the partial numerators are not 1. If a continued fraction has partial numerators that are not 1, we call this a generalized continued fraction. A generalized continued fraction can have any entry in either the partial numerators or the partial denominators. Gauss invented some notation for generalized continued fractions. This symbol works similarly to a summation, where we loop over the index variable and construct the continued fraction inductively. In fact, lots of the results later on are due to Gauss's work, as he was a pioneer in the analysis of continued fractions. For now, we'll focus on simple continued fractions, as the analysis of simple continued fractions is easier to follow, and the analysis of generalized continued fractions follows roughly the same procedure. Going back to our previous example, you might notice that this resembles Euclid's algorithm. As in, we are dividing 1346 by 325, then dividing 325 by the remainder, 46, and so on. In fact, Euclid's algorithm exactly determines the continued fraction for a rational number. The quotients seen in the Euclidean algorithm are exactly the partial denominators seen in the continued fraction, hence the amount of steps taken for a certain rational to get through the Euclidean algorithm is the amount of partial denominators in its continued fraction. In other words, the length of the Euclidean algorithm is the length of the continued fraction. This is in fact the basis for our first proposition. A continued fraction is finite if and only if it represents a rational number. In the forwards direction, we can always start at the bottom of the finite continued fraction and work our way up, evaluating finitely many arithmetic operations on integers. Since we can do this with any finite continued fraction, and as the closure of the integers under finitely many arithmetic operations is the rationals, we can see that every finite continued fraction will be a rational. In the reverse direction, we saw before that partial denominators in the continued fraction correspond to quotients in Euclid's algorithm. So if we can prove that Euclid's algorithm always terminates, this will show that the continued fraction must be finite. To show that this algorithm terminates, Euclid's algorithm essentially generates a sequence of remainders Rk. We can prove that this sequence is strictly decreasing, and every number in the sequence is greater than 0. So this sequence must hit 0, and so the algorithm always terminates. We've characterized all finite continued fractions. I'll try to motivate infinite continued fractions next. An interesting sequence to look at is the Fibonacci numbers. If we look at the ratio between consecutive Fibonacci numbers, we note that the continued fraction representation of these ratios consists of all 1s. This could also be derived by Euclid's algorithm. If we start from the bottom of Euclid's algorithm and work our way up, setting quotients to be 1 at each step, we'd end up with the Fibonacci numbers, and the corresponding continued fraction would consist of only 1s. A classical result states that the ratio between consecutive Fibonacci numbers tends to the golden ratio, phi, which is about 1.618. So we can ask whether an infinite continued fraction, consisting of only ones, also tends to the golden ratio. If we assume this converges for now, we can do some basic algebraic manipulation. Let x be equal to this fraction, and then we can substitute it back inside itself and find x equals 1 plus 1 over x. Rearranging this gives us a quadratic, and its positive solution is the golden ratio. The issue is we have to assume this converges right now, but there is a result later that states all simple continued fractions converge. To prove this theorem, we need to define convergence. Convergence are truncations of infinite continued fractions. We can form a convergent by cutting off an infinite continued fraction, and this yields a finite continued fraction, which we can study more easily. Suppose we have an infinite simple continued fraction with partial denominators ai. We form the kth convergent by cutting off everything after ak. Now, this is a finite continued fraction, and as we saw before, this corresponds to a rational number. We can label the numerator and denominator by pk and qk, so pk over qk is the kth convergent. The first few convergents of our infinite simple continued fraction look like this. You might be able to spot the pattern in the numerator and denominator of this convergent. We can prove this by induction, and with a couple base cases, we end up with the fundamental recurrence for continued fractions. We can do some basic algebraic manipulation and find a couple more identities. The first identity here shows that convergents are in their lowest terms. If there were a number d that divided both pk and qk, then it would also have to divide minus 1 to the k plus 1, so d must be a unit. More importantly, we can look at the difference between consecutive convergents. We see the difference contains a minus 1 to the k term, so this sequence oscillates. If we instead look at the difference between even index convergents, we find they're monotonically increasing. Similarly, if we look at the odd convergents, we find they form a decreasing sequence. Finally, we can prove that all even convergents are less than all odd convergents, and so these two sequences sandwich around a common value. Finally, as the sequence of convergence is Cauchy, the sequence must converge to x. We define the value of an infinite continued fraction as the limit of the sequence of its convergence. So we've shown that all infinite simple continued fractions converge. All this hinged on was the fact that partial denominators are integers. If we wanted to prove something similar for generalized continued fractions, we can also study convergence and find sufficient conditions for their sequence of convergence to converge. We can now try to look at uniqueness of continued fractions. It turns out that rationals do not have entirely unique representation, because we can take its last partial denominator and take away one and add one. Of course, these represent the same number, but the continued fractions are slightly different. To avoid this, we usually use the convention that the last partial denominator should be strictly greater than 1. Now, given this convention, we can prove that all continued fraction representations are unique. First, we have to define tails of a continued fraction. This is essentially the opposite notion to a convergent. We cut off the fraction at the nth entry and take everything below it as the tail. It follows from the recurrence that we have this identity that relates convergence and tails. Now, to prove the theorem, we'll use strong induction. Suppose that x has two continued fraction representations. The base case is quite easy. We can take the floor of both of these representations, and these should give the integer part of x. So now, suppose ai equals ai prime for I up to n minus 1. If we look at the convergence, this also implies pi equals pi prime and qi equals qi prime. Then we can use the above formula and find this equality. So we find that tn equals tn prime. Taking the floor of this gives us an equals an prime, as required. Now that we've covered all the basics, we can start to approach more complex ideas. The first idea I'll describe is Minkowski's question mark function. This function is from real numbers to real numbers. If we express the input as a continued fraction, the question mark function takes in each partial denominator and turns it into a run of zeros and ones. So this generates a binary number. Formally, we could describe it as this sum. We can plot this over the interval 0, 1. We see that the question mark of 0 and 1 are 0 and 1 respectively, and it can be proven that this function is continuous and strictly increasing, and hence this function is a bijection. It also holds that this function is differentiable almost everywhere, and its derivative almost everywhere is 0. This is an example of a fractal curve. In fact, if we rescale it slightly and plot the question mark of x minus x, we find this generates a self-similar fractal. While this function does have interesting properties by itself, it does also have some consequences for number theory. Namely, this is an explicit bijection between non-dyadic rationals and quadratic irrationals, and hence we can prove that quadratic irrationals are countable. This requires a proposition which I'm not going to prove fully. The proposition is that a continued fraction is eventually periodic if and only if it represents a quadratic irrational. We saw an example of this before with the golden ratio. We could substitute it back inside itself and rearrange to get a quadratic. We can see a similar thing going on here with a different periodic continued fraction. For the proof, we'll use the tails formula from before. Suppose that tk is tk plus h, as the fraction is eventually periodic. Then we can use the tails formula and equate these. And then rearranging for tk shows that t must satisfy a quadratic equation, hence x is a quadratic irrational. The backwards proof is non-trivial. Essentially, you look at tails that a quadratic irrational can define and find there's only a finite amount of polynomials that tail can satisfy. The proof can be found in Hardy's book, but I won't go over it here. With this, we can look at Minkowski's function again. Since a rational number has a finite continued fraction, this would correspond to a finite binary expansion under Minkowski's function, and so rational numbers are in bijection with dyadic rationals. Similarly, since quadratic irrationals have eventually periodic continued fractions, these correspond to binary expansions which are eventually repeating, which are exactly non-dyadic rationals. Of course, rationals are countable, so non-dyadic rationals are countable, and hence quadratic irrationals are countable. Another result that combines both measure theory and continued fractions is Khinchin's theorem. It states that the geometric mean of a continued fraction's coefficients almost always tend to this constant. The proof requires ergodic theory, and we'll be using some results from there without proof. The ergodic theorem states that for a measure space with measure mu, an ergodic transformation T that preserves the measure mu, and any f integral with respect to mu, that the average value of f of t to the kx is constant for almost all x. We'll look at the interval 0, 1 without the rationals, so this contains infinite simple continued fractions with a0 equals 0. We define the transformation T on this set, as well as this measure. If we also define the function f that takes in a continued fraction and outputs the logarithm of its first entry, then this is integrable with respect to mu. Finally, it turns out that T is an ergodic transformation, and so we can use the ergodic theorem here. In the first step, we can see that f applied to t to the k yields the log of ak. We can also evaluate the integral on the right, but I'll leave that as an exercise. We can then use log rules to pull the log out of the sum and turn it into a product. Then, taking an exponent on both sides to cancel the log, we recover the geometric mean on the left. Finally, cancelling the exponent and the logarithm give us an exact form for Khinchin's constant. Its value is about 2.6. While we have the result that this theorem holds for almost all infinite continued fractions, we've not proven it for a single number. For example, if we look at the continued fraction of pi, it does seem to tend towards this constant, but we've not proven this fact. We can find a similar result for other constants, like log 2, log 3, zeta of 3, and Khinchin's constant itself. For a counterexample, E does not tend to this. In this last section, we'll look at generalized continued fractions and how we can represent functions as continued fractions. On screen is an example of a generalized continued fraction being plotted. As we graph it to further accuracy, you might notice that it converges on a familiar shape. In fact, this continued fraction converges to tan. Some of these results feature in one of Euler's books. With modern definitions, his work is quite hard to follow, but his chapter on continued fractions is quite fun to read. One result he shows is this identity. His derivation is admittedly quite hard to follow, but this can be proven easily via a double induction. We can use this to generate some continued fraction expansions of elementary functions. For example, if we take e to the x as a Taylor series, we can express it in the form seen in the identity, and this gives us a generalized continued fraction. Of course, one should check convergence, but I won't go over any proofs. A similar method can be taken to find expansions of cos and sine. And then using imaginary numbers, we could derive sinh and cosh. We can also derive an expansion for log x with this. and hence we can find the continued fraction of log 2 and log 3, etc. exactly. We can also look at what Gauss did slightly later. First, he defines a hypergeometric function. This is an incredibly general function. It has 3 parameters, which are given a rising factorial in the series. By inputting specific parameters, we recover lots of elementary functions, so we can see how general this is. More importantly for our purposes, Gauss derived this identity, which relates the hypergeometric function to a generalized continued fraction. For our final result, we can express arctan as a hypergeometric function. Then, applying Gauss's identity, we find a nice continued fraction for arctan, and then evaluating this at x equals 1 gives us a continued fraction for pi.